Welcome to the fourth video of the series of turning AI gears your way. I'm the Tech Emissary, and today we're going to discuss search agents. As I promised in the previous video, we're going to be talking about all the types of search agents, including iterative deepening search and all the other searches. So without further ado, let's dive right in. So we have 5 different searches at the moment. We have breadth first search, depth first search, depth limited search, iterative deepening search, and uniform cost search. So what breadth first search basically does is that it searches first to the shallowest nodes that are available to it before going in deeper. So that is known as one of the basic methods of searching. Generally, we may call it in some times inefficient, but we'll talk more about it later when we talk about it. And we have depth first search, which searches through the deepest nodes that are available to it. So basically, it's going to go from one down one tree before it goes to another tree. And we have the depth limited search. This is a bit of a tweaked version of the depth first search. It searches through the deepest nodes, but with a limit put. So for example, we can put a limit of 2 or a limit of 3 trees that it can search through, basically the layers that it'll search through. Eventually, we have the iterative deepening search, which increases the limit of DLS eventually. So basically, we can increase the limit as we go along the depth limited search. That's what an iterative deepening search is. And finally, we have uniform cost search, which searches the least cost nodes basically. And this is very important because sometimes other search methods may find pathways they think are short, but are actually the most costly or are not the cheapest. Uniform cost search wants to try to go through the paths that are always the ones that have the least weight, as people may call it, because we will place weights on paths depending on their costs, and that's basically what we want to minimize in uniform cost search. So firstly, we're going to go through the breadth first search. So we first search all possible nodes. That is, if the branches are finite. So basically, it is very important because we need to be able to know how many nodes are there as well. So as long as it is finite, we can find it, because if it's infinite, it'll take an insanely long amount of time, if nearly impossible. If it's infinite, of course, it's impossible. But if it's a really big number, it's really hard to be able to do that because it'll take a really long time. So is it optimal? It depends, really, because sometimes it can be optimal in some cases, sometimes it's not. It depends on what situation we're using it for, and we'll see through a demonstration I'll show later. And the space taken up is basically the function of b to the power of d, and basically the time taken will be shown by polynomials. So we first have, for example, like 1 plus a to the power of 1, eventually a to the power of 2. Eventually this will keep increasing because this is basically going to represent time taken as we have more nodes, and especially since we have more branches. Now, let's look at the BFS properties for search based on branching factor b equals 10, 1 million nodes per second, and 1000 bytes per node. So when we start with smaller numbers of depth, you can see when we get to the depth of 2, we have 110 nodes, 0.11 milliseconds, and 107 kilobytes. That's still good. Good timing, good memory taken, still good. But when we get to a depth of 4, we have 11,110 nodes, and we will take a time of 11 milliseconds, and a memory of 10.6 megabytes. That's still understandable. However, if we go to a depth of 16, you can see that we have 10 to the power of 6 nodes being searched, 350 years of time taken, and a memory needed of 10 exabytes. So that's crazy. You would die before probably getting those number of nodes being searched. Of course, if you found a way to prolong your life, just like those movies where you try to find immortality and stuff like that. But anyway, we can see that this is clearly a lost cause. So we have to move on to the next possible methods that could actually solve this. How about depth first search? Let's take a look at this. It can finish a finite search, but it cannot finish an infinite search. Same as BFS. of course, because we can't possibly search through an infinite amount of nodes. We need a stopping point. And eventually, the time taken will also be consumed more or less the same as BFS because we also search through all the nodes. And it'll take a time of function of b to the power of d as well, just like BFS, but it can be faster if solutions are dense. And the time taken up, the space taken up, will be a function of b times m, and essentially, it's not optimal. This can be called optimal in some cases, but in most cases, it's not optimal. But we'll look also as well in the implementation to see why this is. But however, one of the biggest improvements here is that we can see that there's a big improvement in memory. Although it consumes the same time of 350 years, it manages to reduce the memory needed from 10 exabytes to 156 kilobytes only. So you can see the big improvement there of why we would choose to use depth first search instead of breadth first search, although the time is the same. So essentially, if you don't make it to 350 years, you'd still be happy with the thought that you already have saved a lot of memory. Oh, that's actually not a good thought, so you can just let that go. So going to the next bit, depth limited search. So basically what we were doing here is that we were putting a limit L to DFS search, and eventually we'll be able to increase the limit, but this is for iterative deepening search, which we'll eventually discuss. And eventually we go to iterative deepening. Basically, we have an iterative nature of expanding until the shallowest solution depth is reached. So this is an expansion from DLS, except that we're using it with increasing limits. And to get a better understanding of it, I'll just show it directly in the next examples that will happen. Uniform cost search. So basically, we are going with the cheapest as opposed to the shortest. So we want to find the cheapest paths that would cost us the least. And eventually we have this idea of applying weights to each of these paths. So through applying weights, it'll be able to search through the weights instead of just looking at which path is shorter. So this is very important when we're trying to travel from one location to another, for example. We would of course look at the ticket price, for example. If we were going through an airplane, we would look at if the ticket from Jakarta to Singapore would be cheaper when we're trying to reach Hong Kong rather than going from Jakarta to Thailand and then Hong Kong. So that's just one thing that we can do. Of course, I'm not just saying this based on real data. This is just assuming. So the next thing is we can explore by costs that may be increasing. So we can explore the costs, and eventually we will see that it'll eventually go to seeing the increase in cost that may happen in other nodes as well. So this is important, and we will be able to explore in every direction this way. So basically, the uniform cost search will complete if the number of things that it searches is finite, as usual. The time taken will be a function of the O, B to the power of C optimal divided by epsilon. This is where C optimal is the cost of the optimal solution, and epsilon is basically the cost based on the bound. So every action costs at least epsilon. So basically this is going to be the effective depth, or how deep the cheapest solution will be. So that's how we get the function O, B to the power of C optimal divided by epsilon. So the space will also be the same, and eventually this will be an optimal solution because we're able to search the possible nodes and find the optimal solution. Instead of the shortest path, we find the cost-effective path, and that's what we want. So we're going to be using our Google tree example to be able to illustrate what I have previously just said about all the 5 different searches. So let's try it out. Firstly, in breadth first search, as you can see, we first tackle what is directly below A, or the first node. So we're able to see that it directly searches in the first layer, and eventually it'll go to the next layers. So this is important, as we can see the illustration over here. But of course, it differs from the depth first search. As you can see over here, it'll first tackle the first area, B. Then you can see it searches the nodes below that, and if it has nodes below that, it'll also go below the nodes as well. So you can see that it'll first tackle that tree, and eventually move on to C, eventually move on to D, and the nodes below them. So that's an example of depth first search. Going to iterative deepening, so you can see that with limit 1, it'll search in the first sector first. So don't confuse this with breadth first search. This is because we are placing a limit 1, so it'll only search in the first layer, and it'll only be limited to the first layer. And this is just a case of the previous DFS, except that the fact that we are limiting it to being only searched in layer 1 up to layer 1. And eventually we have the uniform cost search example. So you can see over here, we have the various costs being put on the weights, as we can see over here, and eventually we have the nodes here. So a breadth first search algorithm may suggest you to go A, B, C, F. However, a uniform cost search would suggest you to go from A to D to E to F, because the weights are basically the lowest there. They're trying to minimize the cost, so that's basically what we want. And that's the end of the video. So I hope you're ready for the next video, because it's going to be a lot of fun. It's going to be a practical. I'm going to tell you what the practical is going to be about on the video. So I hope you're ready for it. And I hope that these concepts have been able to help you understand much more regarding AI and to get ready for the practical, because the practical is going to require all these theory as well as some fundamentals that you may have learned at high school perhaps or university level. So you better get ready for it. It's going to be a lot of fun. So I wish you the best, good luck, and I'll see you in the next video. Thank you.